Hi everyone, this is Lin Chao from UT Dallas and my advisor is Lin Ming. Fosu and Xiaoying are from UT San Antonio. Today I'm going to present my XC20 paper, Taming Behavior Backward Incompatibility with Cross-Project Testing and Analysis. First, let me introduce what's the backward compatibility. It's widespread in both commercial and open source libraries. When a library gets upgraded, some changes can break the existing functionality. For example, there is the old version includes some API. When it upgrades to the new version, some API change, some API may not. The bugs due to this change, we call it backwards incompatibility bug. And the problem is very hard to detect and have serious impact. And recently, there is a news named another one-line npm package broke the JavaScript ecosystem. According to the GitHub, there are more than 3.4 million projects affected and 766 JavaScript libraries get involved, like Facebook, Google Map, Firebase, and Amazon all involved in this issue. And usually developers will use regression tests, rerun all the tests after upgrading to check if changes break the existing functionality or not. And here is an example from Commons VFS, which upgrade from 2.2 to the 2.6. And there are some test cases and the API is covered. However, from our experience, we detect the URL file name parser have a BBI bug, but it cannot detect it by just run the original test. And here is the repository growth graph for the Maven repository and GitHub repository. Until now, there are tens of millions open source projects we can use. So we propose our technique, DBBI. We use cross-project testing and analysis, which means we use a large number of high-quality client project tests from other projects. However, it involves a huge testing effort. So we further use information retrieval to rank those projects. Then we transform the BBI bug to our IR problem. Here is an example from VFS 2.2, and here are some client projects and the test cases and the library's usage in this test. And when it upgrades to VFS 2.6, the URL name parser gets changes. So we run all the tests in all the client project which touch this change. And here is the overview of our DBBI. We have three parts. We generate the index from source code as document. Meanwhile, we generate diff changes as query. And then we retrieve which project could be the most relevant one may have BBI bug. And for the query generation part, we extract the class of file level changes between the old version and new version as query. And we have two versions of library and get diff information and get class changes. Due to the space limit, we only show the class name here. In fact, we extract the whole package name into query document and we construct our query. And for the index generation part, we use static analysis to extract the library usage of each project as document. And we have a bunch of source code files from client project, and we analyze them, get the library usage, and we construct them into the document. And for retrieval, we use traditional information retrieval to prioritize the projects. And we have our diff include two changed API, and there are three projects, P1, P2, and P3, and P2 is more relevant to this diff. So after the retrieval, we execute P2, P3, and P1. And for the first optimization with the diversity, we use information retrieval with MMR to increase the diversity. MMR is an algorithm which can solve the diversity issue to improve IR performance. And we still have a diff include 4 changed API, and we have P1, P2, and P3. P1, P2 share the same API use and they are most relevant to this diff. If we use the traditional IR, then P1, P2 should have a higher rank. But because they share the same API use, then the bug behind them might be the same. So after MMR with IR, our execution order would be the P1, P3, and P2. Then we can earlier detect the different type of BBI bug. And our second optimization is use the regression test selection. We use static analysis to get the dependency of each test and only execute the affected test. And we have 3 projects here. And after the RTS, we only execute the affected test T2 in P2, T1 in P3, and none of the tests touched get affected in P1, so none of the tests execute here. And for our experiment data set, we use nearly 3,000 in GTK experiments and 100 libraries and around 40,000 open source GitHub projects for our third-party library experiment. And there are three metrics in our evaluation part. The first, average, and last. We report the time taken, number of projects, and number of tests executed to identify the first, each, and the last BBI bug. And here is the improvement for our GTK test execution. There are 4 techniques, random as the benchmark, LDA, LDA with MMR, LDA with MMR, and RTS. Cluster here means we target on each different type of BBI bug. And through the graph, we can see we have a huge improvement. And we detected 97 bugs and report to the developers, 54 confirmed as known bug and 19 confirmed as unknown bug. And here is the overview of our detected unknown bug. And this is the first example bug from our third core. The method contains only keys, cannot handle the case when it involves our map with the key tab is passed. So we construct our tab and put the key with the tab pass and try to call the method contains only keys. Then this test fails. Here is the second example bug from Commons BFS. The method pass UI will fail to pass UI when the first 2 parameters are both none and the UI includes a substring like this. So we construct our string like this and put the first and second parameter as none and try to call this method, and the test failed. And here is the third example from GSoup. The developer forgot to deal with the situation when the end of the string in method select is a space. So we construct our string and end with a space and try to call the method select, then the test failed again. So for all of those test cases are from real-world projects, which are hard to generate by the automatic test generation tool. And here is the conclusion from our paper. We leverage cross-project testing and analysis to detect BBI. And we transform the BBI detection problem into a traditional error problem. And we further optimize using the diversity and cross-project RTS to further speed up the detection. And we discovered 97 bugs for the real-world libraries, and 19 are the previous unknown bugs. So that's all. Thank you.